A microphone can hear a whisper. So why can that tiny signal end up shaking a stadium speaker like an earthquake? Here's the trick. An amplifier doesn't create power from nothing. It uses a small signal to control a much bigger flow of energy coming from a power supply, like a valve. Think about a faucet. Your fingers don't provide the water pressure. They just set the opening. The pressure comes from the plumbing. An amplifier works the same way. The input signal is the hand on the valve, and the power supply is the pressurized source. So where does the big energy actually come from? From the wall outlet or a battery. Inside the amplifier, that energy is converted into steady electrical reservoirs, clean DC rails that just sit there, ready. The amplifier's job is to take that stored energy and release it in the exact shape of the input waveform. That's what gain really means. If the input is a small wiggle, the output is the same wiggle, just bigger. But bigger can mean different things. Sometimes you want more voltage, a taller waveform. Sometimes you need more current because the load is hungry. A speaker is the classic hungry load. It's basically an electromagnet attached to a heavy cone. To move it with authority, you need real current. That's why a headphone amp and a speaker amp aren't the same beast, even if the music is the same. At the heart of most amplifiers is a component acting like that valve, a transistor, or a set of them. A transistor lets a small change at its control terminal cause a much larger change in the current it allows to pass. Small input, big controlled output. But there's a catch. To amplify smoothly, that valve must already be partially open. That's called biasing. If you start fully closed, half the waveform tries to go negative and the transistor just shuts off. You don't get a clean amplified copy, you get a chopped, lopsided mess. Biasing sets a resting point so the signal can swing up and down inside a controllable region. And that leads to the word that separates great amplifiers from trash ones, linearity. A linear amplifier makes the output a faithful scaled version of the input. But if you push too hard, the device becomes nonlinear. The waveform starts to warp, and your clean tone picks up extra frequencies that weren't there before, distortion. Push it even harder and you hit the rails. The amplifier can only swing as far as its power supply allows. Once the output reaches that limit, it can't go higher, even if the input keeps demanding it. So the tops of the waveform flatten. That's clipping. And clipping doesn't just sound harsh, it can dump extra heating into speakers because it adds lots of high-frequency energy and keeps the system pinned near extremes. So how do good amplifiers stay accurate when real parts are imperfect? They cheat, in a smart way, using feedback. The amp samples its own output, compares it to what the input asked for, and corrects the difference. It's like cruise control. The car doesn't magically become perfect, it just constantly measures error and pushes back against it. Now, accuracy has a cost: heat. Anytime the amplifier is dropping voltage while pushing current, it's burning power internally. That becomes heat in the output devices and heat sinks. That's why different amplifier styles exist. Some designs stay in a wasteful but smooth mode a lot of the time. Others split the job between devices so each one works less. And modern switching amplifiers can be extremely efficient by rapidly turning devices fully on or fully off, then smoothing the result back into audio for the speaker. Different approaches, same goal, control power without wrecking the signal. So the full story is simple: a tiny signal doesn't become big by magic. It becomes big because it commands a bigger energy source, shaping power from the supply into a stronger copy of the original waveform. Now your turn. What should we break down next? Speakers, microphones, or why distortion can sound good in guitar amps?